Hi, let's take a look at Chapter 4 and review it briefly. Section 4.1 began the chapter with the talk of exponential functions, and if you recall, an exponential function is a graph of the form y is equal to a to the x, where a has to be greater than 0 and a cannot be 1. So whenever we look at the graph of this, like for instance y is equal to 2 to the x, y is equal to 3 to the x, and so on, we get that the shape looks like this, where it always has an y-intercept of 0, 1, and there is a horizontal asymptote at y is equal to 0. Okay, so again there's that imaginary line that the graph cannot cross in this case, because 2 to any power is always positive. It gets really small and gets really close to 0, but it never does touch it. Now, it looks in this form, that's called exponential growth, and that's when actually a is greater than 1. When a is between 0 and 1, like for instance y is equal to 1/2 to the x, or y is equal to 1/3 to the x, the graph looks the same except that it's really a reflection across the y-axis, and it looks like this. It still has the same intercept of 0, 1, and it still has the same horizontal asymptote of y is equal to 0. Why is it a reflection? Well, remember 1/2 really is 2 to the negative 1 to the x, so this is something that's really just 2 to the negative x. So these graphs are transformations of one another, which are just reflections across the y-axis. Okay? Now, you should be able to do exactly that, that is, transform some of these graphs and identify the domain and range and also the asymptote. So let's just talk about that briefly here. What is the domain and range of these functions? Well, the domain of an exponential function is all reals. I can put anything into the power that I want, but the output is only going to be from 0 to infinity. And that's the case for either exponential growth or exponential decay, is what's represented here. Okay. So, like for instance, if you have, go to another page, number 27 on page 337 is g of x is equal to 2 to the x minus 3. So it takes that basic function that we just had and it's going to shift it how? Yeah, the minus 3 is what I call an outside change. It's going to shift it down 3 units. So that means I'm going to have a horizontal asymptote at y is equal to negative 3. And my intercept also shifted down. So remember it was at 0, 1. I'm going to have to go down 3 units to 0, negative 2. And this would be the graph. Okay. So my domain is still all reals, but my range is at negative 3, not including to infinity. Okay. And I'll let you play around with the transformations. The transformations are just the same. You're just now shifting this basic function. So you would just add this to your other collection of functions that you know. Okay, let's talk about section 4.2, which is logarithmic functions. Okay. And how did logarithmic functions arise? Well, they were actually arose from exponential functions. They are in fact the inverse of an exponential function. So if we have y is equal to a to the x, this is equivalent to log base a of y is equal to x. Okay, so the base of the exponential function is the base of the logarithmic function, and a logarithm is nothing more than an exponent. Okay, so you really need to know this connection. I'll state it again. Log base a of y is equal to x is equivalent to y is equal to a to the x. In fact, I do it more like the book. If I start with the log function, then the way I convert it to the exponential, say a to the x is equal to y. Okay. So you should be able to go from one form to the other, the log form to the exponential form, and vice versa. So for instance, if you're told log base 8 of 1/8 is equal to -1, well, in exponential form, that means 8 to the -1 is equal to 1/8. If you're given 4 to the third power is equal to 64, to convert it to the log form means the log base 4 of 64 is equal to 3. Okay. Now, how can you evaluate some of these expressions? You really need to remember some of the basic properties of logs. Do you remember that if you have the log base b of b, that's always equal to 1. That's because b to the first power is b. The log base b of 1 is always equal to 0 because b to the 0 is 1. The log base b of a negative number is always undefined because when we raise b to any power, we're always going to get something that's greater than 0, never negative. Okay. And then what about, we have log base b of b to the x. That's just simply x because b to the x is equal to b to the x. Okay, so really when you're trying to evaluate a log, like if I had log base 2 of 8, I'm asking myself what power of 2 is producing 8? So that's 3. Okay, so you're really thinking about what power of b is producing b to the x, and that would just be x. And then the other things you should remember is that the log base 10 of x is a common log, and it's sometimes just written log of x. And the log base e of x is a natural log, and it's written ln of x. So if I wanted to evaluate, let me do one more. Log base 9 of like the square root of 3. Let's call it y. This is actually number 20, part C. I'm asking myself 9 to what power is equal to the square root of 3. So one way to do this is to get 9 and the square root of 3 in the same base. So 9 is really 3 squared. So I really have 3 squared to the y. The square root of 3 is really 3 to the 1/2. So this is nothing more than 3 to the 2y is equal to 3 to the 1/2. So since the bases are equal, my powers have to be the same. So 2y is equal to 1/2. And if I divide both sides by 2, I would get y is equal to 1/4. Okay. Now the graph of the log function, let me come back up here where I had a blank page. The graph of the log function is symmetric with respect to the y-axis of the graph of the, I'm sorry, not symmetric with respect to the line y equals x. It is the inverse of the exponential, and so the x and y change roles, right? So if I looked at the graph of y is equal to a to the x, to get the log graph, instead of a horizontal asymptote, I'm going to have a vertical asymptote. And instead of the point 0, 1, I'm going to have the point 1, 0 as a key point. And my domain and range change. My domain is from 0 to infinity, and my range is from negative infinity to infinity. Okay? So this is y is equal to the log base b of x, or log base a, whichever one you want to say it. Okay, so for this one you had to use some of the just rules of definitions of logs. There were some problems where you had to use transformations to draw the graph of the function, matching the graphs of the functions, and you really didn't get into any of the applications with that. So if you have, oh well, and then there were some where you had to find the domain. So let me just talk about that real quickly. Like problems 59 through 63 or so, like let's do 62 because that's a little bit more complicated. It's y is equal to the natural log of x minus x squared. Well, the domain of a log function, the input or argument always has to be greater than 0. So there I need to find where x minus x squared is greater than 0. If I'm doing that by hand, I have to find where x minus x squared is equal to 0. And if I factor out an x, that's not going to be, if I factor out an x, I would get 1 minus x is equal to 0. So x is equal to 0 or x is equal to 1. And then I'd have to use boundary numbers to solve this because this is a quadratic inequality I'm solving to find the domain of the log function. And then I'd have to test points to see where is this expression true or false from the numbers on the number line. So let's say if I put in a -1 from that first region, so -1 minus what? -1 squared is 1, so that's a -2. Is that greater than 0? No. If I put in like a 2 in my other region, is 2 minus 2 squared greater than 0? No, that's 2 minus 4, which is -2, which is not greater than 0. So if we test in the middle region, we'd have to put in like a 1/2. So it's 1/2 minus 1/2 squared greater than 0. That'd be 1/2 minus 1/4. And 1/2 is 2/4 minus 1/4 is 1/4, which is greater than 0. So that's true between the values of 0 and 1. We can't include the endpoints because it's strictly greater than. So the domain of this function is going to be the interval from 0 to 1. Okay, so if you have any questions on that, don't hesitate to contact me. Then we want to go on to the last section you had to cover, which was modeling with exponential functions. And I just want to work a few of these to make sure you're understanding it. So our model, we're always going to come up with n of t is equal to n sub 0 times e to the r. T is what our model is. Okay, so we're putting everything in terms of the base e. So let's look at, for instance, number 7. In your book, page 380. So it's given us a graph that shows the deer population in a Pennsylvania county between 1996 and 2000. Assume the population grows exponentially. Part A says what was the population in 1996, and notice that on the graph T is a year since 1996, so the population in 1996. We're trying to find what is the y value when T is 0. Or in other words, the y-intercept, or the n-intercept in this case because of the way they have the axes labeled. But notice that the point 0, 20,000 is on the graph. So that tells us that the population was 20,000. Part B says to find a function that models the deer population t years after 1996. So we know the initial value was 20,000. And then we're also given another point on the graph. We're given the point 4, 31,000. So what we are to do is to use this model with n sub 0 as our initial value. And we're going to plug in the value of t and n of t, and really think of that as an x, y, and try to solve for the value of r. So we are going to have n of t is equal to n sub 0 times e to the rt. N of t, that is our output, is 31,000. Our initial value is 20,000. E to the r we don't know, but we do know t in that case is 4. So we would have to divide both sides by 20,000. We're going to get 1.55 is equal to e to the 4r. So now this is where we're going to use the property of logs to bring down the exponent. If we take the natural log of both sides, we're going to get the natural log of 1.55 is equal to just 4r. So if we divide both sides by 4, we're going to figure out what r is. So if we take the natural log of 1.55, divide by 4, okay, we're going to find that r is 0.1096. And notice that r should be positive because this is modeling exponential growth, not exponential decay. So we know that our model is n of t is equal to 20,000 because we knew our initial value, times e to the 0.1096 t. So we can use that to answer part C, what is the projected deer population in 2004? So 2004 is how many years after 1996? Eight years, so we could plug in 8 into this model. I'm running out of room here to figure out what that's going to be. So on the calculator we would have 20,000 times e to the 0.1096 times 8, then close the parentheses, and we would get 48,064 about. And in what year will the population reach 100,000? So we have to set the function equal to 100,000. So if you set 100,000 equal to 20,000 times e to the 0.1096 t, you'd have to divide both sides by 20,000. So you get 5 is equal to e to the 0.1096 t, and then take the natural log of both sides. So that you get the natural log of 5 is equal to 0.1096 t. So then divide both sides by 0.1096. So the natural log of 5 divided by 0.1096. So that is 14.7 roughly. Okay, so in 14 years after 1996, which is the year 2010. Okay. Now let me look at one like number 15, radioactive cesium. So the half-life of cesium-137 is 30 years. Suppose we have a 10-gram sample. Find a function that models the mass remaining after t years. So if we know the half-life is 30 years, and we know that we start with a 10-gram sample. Now your book actually shows you a way to calculate the coefficient of decay. I would say you don't really have to memorize that. If you know this form, n of t is equal to n sub 0 times e to the rt, you can always figure it out. Because our half-life is 30, means that if we start with 10 grams, in 30 years we're going to only have 5 grams remaining. So if our initial value is 10, our output's going to be 5 after 30 years. So if we divide both sides by 10, we would get 5/10, or just 0.5, which is 1/2, is equal to e to the 30r. So if we take the natural log of both sides, we're going to get that the natural log of 0.5 is just 30r. Then divide by 30. And so the natural log of 0.5 divided by 30 is a negative 0.2. Oops, I left out my 0. Sorry about that. Okay, so the model for this is n of t is equal to 10 times e to the negative 0.023 times t. Then how much will remain after 80 years? You would put 80 in for t and use your calculator to evaluate that. So we'd have 80 times negative 0.023. So you get 1.59, 1.6 grams remaining. How long will it take for only 2 grams to remain? That's where you're going to set 2 equal to this. Dividing both sides by 10, 2/10 is really just 0.2. And then take the natural log of both sides, so you'd have the natural log of 0.2 divided by negative 0.023 and get about 70 years for that to happen. Okay? And let me do one more, like number, well, yeah, 22. Talks about carbon-14 dating, and it says a wooden artifact, I'm sorry, this is 21. A wooden artifact from an ancient tomb contains 65% of the carbon-14 that is present in living trees. How long ago was the artifact made? And we're told that the half-life of carbon-14 is 5,730 years. Okay, and so we know 65% of the initial amount remains. So the way you're going to do this, you don't know what the initial amount is, but you do know that 65% of it remains, so 0.65 times n sub 0 is what remains. So we would have n is equal to n sub 0 times e to the RT. So our n, our output value, is 0.65 n sub 0 is equal to n sub 0 times e to the RT. Okay, and we don't know what R is yet. I need to back up and find that. The way we're going to find R is use our half-life. And you could use a formula again in the book, but I'm just going to say to work it out. So we know that if we have half of our remaining amount in 5,730 years. So if we divide both sides by n sub 0, we would just get 0.5 is equal to e to the 5,730 r, taking the natural log of both sides. We're going to get the natural log of 0.5 is equal to 5,730 r. So on the calculator we need to divide natural log of 0.5 by the half-life, which is 5,730. Okay, this is negative 1.20968 so on times e to the negative 4, which means negative 1.20968 times 10 to the negative 4. So it's scientific notation. So to convert it out of scientific notation, we have to move the decimal point 4 places to the left, which is going to make that a negative 0.00012. 1 will round off there. Is our value of r. So we really have, back into our equation that we're trying to solve, 0.65 n sub 0 is equal to n sub 0 times e to the negative 0.000121 t. So now we can divide both sides by the ends of 0. So we get 0.65 is equal to e to the negative 0.000121t. And then using our natural log, thank goodness for the natural log, that brings this exponent down. So we get natural log of 0.65 is equal to whatever this coefficient or exponent was, 0.000121t. Dividing both sides by that ugly number, we're going to get the natural log of 0.65 divided by negative 0.000121. Make sure you get enough zeros in there. And that's going to be 3,560. Okay. So the artifact was made 3,560 years ago. Okay, so that's chapter 4 in a nutshell. If you have any questions, please contact me.